Pluto is a far-off and covert, more unobtrusive planet that was once a piece of our close-by planetary framework. However, ongoing upsetting explanations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have carried Pluto back into the spotlight with a stunning disclosure. They propose that this crisp world is on a potential impact course with Neptune. But how is it that this could work out, and what may be the outcomes of such a monstrous occasion? Are we seeing a charming, enormous peculiarity, or is there another thing to this oncoming divine mishap? Join us as we investigate the possible consequences of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet partly because of its surprising orbit, remains a subject of interest and study in the astronomical community. According to ongoing conjectures by leading scientists, Pluto's orbit is hazardously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential, risky crash between these two planets, which could pose a gigantic danger to Earth. But how is such an event even conceivable? Pluto's orbit around the Sun is unlike that of any other planet in our solar system. It requires a shocking 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, wandering widely from the nearly round orbits of the major planets. What makes Pluto's orbit even more unique is its inclination, set at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more tilted compared to other planets. This inclination and unpredictability add layers of complexity to its orbital pattern. One of the most captivating aspects of Pluto's orbit is its intersection with Neptune's orbit. For about 20 years in each orbit, Pluto actually comes closer to the Sun than Neptune, defying what we might expect from their positions in the nearby planetary system. This leads to the natural question, why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unusual path. Unlike other planets, whose orbits lie mostly near the ecliptic plane, Pluto's orbit stood out with its steep inclination and elongated shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is evidence of the intricacies of space mechanics. The three-body problem in space involves determining how three objects, like Pluto, Neptune, and the Sun, move and interact with each other through gravity. It's like trying to predict where they will go based on where they start and how they pull on each other. For Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex manner. The terms ASU libration and degree libration, along with the V's-K oscillation, are part of this puzzle. According to astrophysicists, what keeps all planets in their orbits is ASU libration. As for Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is positioned no less than 90 degrees away from Neptune. This spatial division is crucial in keeping their orbits from intersecting. Degree libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential collisions. Another significant aspect in this situation is the V's-K oscillation, named after three researchers, V, Zell, and Kai, who studied how objects move in space. It involves how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This gravitational pull affects how they move. For Pluto's case, the V's-K oscillation helps us understand why its orbit around the Sun is so unusual. Despite Pluto's orbit appearing irregular, this oscillation ensures it moves smoothly over long stretches of time. The V's-K oscillation shows that, although things in space may seem chaotic and unusual, certain patterns and forces keep everything in order. These factors help maintain Pluto's orbit stability, ensuring that it doesn't crash into Neptune or drift off course. This three-body problem is crucial for understanding how these orbits change due to the way space objects interact with each other. Studying this helps us learn more about Pluto and our solar system, as well as distant planets and their stars. Numerical simulations in the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is indeed wild, with slight deviations in initial conditions leading to massive changes over millennia. Nevertheless, these striking properties of Pluto's orbit have been found to maintain stability over incredibly long time scales. Monitoring the disturbance, later computational models have helped us understand how giant planets like Neptune, Jupiter, and Saturn affect Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only player. Jupiter's gravity also plays a critical role in stabilizing Pluto's orbit, as does Saturn. These simulations show that Jupiter's gravity alone is strong enough to ensure Pluto remains on a steady path for a long time, possibly even millions of years. So perhaps Neptune, Jupiter, and Saturn are working together to ensure Pluto continues to move safely in space without running into trouble. These quirks are essential in keeping order and stability in space. Without these factors, the solar system as we know it would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, especially with discussions about it potentially colliding with Neptune in the future, understanding its orbit is critical. This provides a clearer picture of the dynamic nature of the nearby planetary system. The case of Pluto demonstrates how even the most seemingly unstable orbits can reach a state of equilibrium through the intricate interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our position in the universe. Investigating the depths of space often leads us to confront the strange nature of celestial bodies, and Pluto's orbit is a perfect example of this oddity. The concept of orbital chaos, which refers to the sensitive dependence of a celestial body's orbit on its initial conditions, is clearly illustrated. For Pluto, this means that even slight changes in the dwarf planet's position or speed can radically alter its long-term orbit. Using computational models has been immensely helpful for scientists in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects, like Neptune, pull on each other. By tweaking small details in the simulations, astronomers can see how even tiny changes can have a huge effect on where Pluto ends up. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having elements like AIML and scope vibration to keep it stable, its orbit can still be eccentric and chaotic. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after many years. However, even with this chaos, Pluto's orbit remains stable over incredibly long periods, like billions of years. This means that Pluto's journey around the Sun has a sort of order to it, even though it seems turbulent at first. Predicting celestial events, especially when they involve erratic orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While numerical models provide valuable tools to understand and predict the future paths of celestial bodies, they also highlight the limits of our predictive capabilities. These models heavily rely on the accuracy of initial conditions, and any small error or distortion can lead to vastly different outcomes, making precise predictions an overwhelming task. Moreover, the turbulent nature of planetary orbits, like Pluto's, reminds us of the ever-changing and dynamic nature of the universe. While we've made enormous strides in understanding space, Pluto's case serves as a humbling reminder of how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides important insights into the broader dynamics of the nearby planetary system. It shows how the presence and position of each planet can significantly influence the stability and direction of other bodies within the system. So, why are prominent astrophysicists recently raising concerns about a potential collision between Pluto and Neptune? Despite all these complex forces trying to prevent such an event from happening, Neil deGrasse Tyson, a prominent astrophysicist and a major figure in advancing cosmology, offers a compelling perspective on the mysteries of our planetary system, especially the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving nature of celestial mechanics and the public's interest in the neglected realms of space. Tyson's stance on Pluto's renaming is based on the ever-expanding knowledge of our nearby planetary system. He views the renaming not as a downgrade, but as a significant change in our understanding. Tyson views the renaming of Pluto as a necessary shift in understanding, reflecting the growing body of knowledge about our solar system. As our tools and methods for observing the cosmos have improved, so too has our ability to categorize celestial bodies more accurately. This process of redefining Pluto and other objects like it reflects the dynamic nature of scientific discovery, where our views evolve as new evidence comes to light. While some see Pluto's demotion as a loss, others, like Tyson, argue that it represents an important step forward in refining how we understand the cosmos. Additionally, Tyson and other leading astrophysicists have emphasized that, even though Pluto's status may have changed, it remains a fascinating object of study. The complexity of its orbit, the peculiarities of its interactions with other planets, and its mysterious nature all continue to intrigue scientists. In fact, as technology advances, we are likely to learn even more about Pluto's past, present, and future, including how it could interact with Neptune or other distant objects in the future. While the potential for a Pluto-Neptune collision may sound alarming, it is important to remember that the gravitational forces acting on Pluto and Neptune have kept their orbits stable for billions of years. The complex interplay of these forces ensures that, for now, Pluto will continue on its strange and unpredictable journey around the Sun. Still, it is crucial for astronomers to monitor the situation closely, as even small changes in the positions or movements of these bodies could lead to unexpected outcomes. In the end, the ongoing study of Pluto and its interactions with the rest of the solar system offers valuable insights not only into the mechanics of our planetary system, but also into the broader workings of the universe. By examining these distant worlds and their orbits, we gain a deeper understanding of the fundamental laws of physics, the dynamics of gravitational forces, and the unpredictable nature of space. While a potential collision between Pluto and Neptune may be unlikely, the continued exploration of these celestial bodies helps us refine our models, improve our predictions, and deepen our appreciation for the mysteries of the cosmos. In conclusion, the question of whether Pluto could collide with Neptune remains an intriguing puzzle. Thanks to the efforts of scientists and astrophysicists, we now understand that while the two planets' orbits may cross, a collision is highly unlikely due to the complex forces at play. Yet, as our knowledge of space continues to evolve, so too will our understanding of these far-off worlds and the cosmic forces that shape their paths. Ultimately, the study of Pluto and its unique orbit will continue to captivate and challenge astronomers, offering new insights into the dynamic and ever-changing nature of our universe.